everyone. So it was voted, I mean, we have little votes on the Discord, and vector spaces got voted for. They were a popular topic, I guess maybe because everyone knows what they are. So let's do vector spaces. And the way I'm gonna do two things. Firstly, I'm gonna show you how to make subspaces. Oh, so firstly, let's import tactics, because we can't get anywhere without tactics. And let's import the theory of finite dimensional vector spaces. Import linear algebra, finite dimensional. There we go. So this is all the tactics. And this is finite dimensional vector spaces. There. And where are we going to start? Well, so, you know, somehow goal today, somebody called David Jordan emailed me a couple of weeks ago and asked whether Lean could do kind of undergraduate problems in the theory of vector spaces. And he picked up a random problem sheet that he gives his students in Edinburgh, and it was to prove that the intersection of two 5-dimensional vector spaces, 5-dimensional subspace of a 9-dimensional vector space was non-zero. So I said that this could be done, and today I'm going to show you how to do it. But before I do it, I will set up a theory of subspaces of vector spaces. Now, this theory already exists in Lean, so let me get rid of that. Let me make this a bit bigger. So goal today, prove that the intersection of two 5-dimensional subspaces of a 9-dimensional space is non-empty, is non-zero. It's obviously not empty because it contains the origin. I've got to prove it's non-zero. But before we do that, before we start on this, I will show you, let's start to develop a basic interface for subspaces of a vector space. So as I say, this has already been done. If I should be able to check, there'll be something called subspace. Yes, you see, there's already something called a subspace. And can we make sense of it? What does this subspace say? It takes R, which is a field. So given a field and given an additive so let R be a field and let M be an additive commutative group, and assume that M is a vector space over R. You know, then subspace is some type, right? So I don't want to use those. I just want to show you what goes into making the theory of subspaces. So let's go into a namespace, and now I don't have subspace anymore, right? Check subspace. So there. I do have a subspace. Let me define subspaces anyway. So let's make a new structure. So what's going on here? So I'm going to let K be a field. So K is a type with a field structure, and let's let V be a vector space over K. So V is a type with a vector space structure, and to give it a vector space structure, first of all, you need to give it an additive commutative group structure there, and then secondly, you give it a vector space structure there. And this is now going to be defined to be, so what is, oh, it hasn't got a name, structure subspace. There you go. So K is a field. So this says, yeah, we're going to define the structure of subspaces of the K vector space V. And so what is a subspace of the K vector space V? So this is subspaces of a K vector space V. And a subspace will be, first of all, it's a set, right? Which traditionally, for some reason, is called the carrier. So that's a subset of V. So what is a subspace? A subspace of V is a subset of V. And it's slightly unfortunate that that's called, I mean, this should really be called subset, I think. I don't really understand why it's not called subset. But for some reason in Lean it's called set. Set V is the type of subsets of V. Okay, so we just have to get used to it as mathematicians. So a subspace of V is a subset of V which contains 0. So now these are axioms. So let's call it 0 mem. That would say that the 0 vector in V is in carrier. And what else? And is closed under addition. So this would say add mem. I guess that would say for all A and B in V, if A is in carrier and B is in carrier, then A plus B is in carrier there, and is closed. And the other thing is closed under scalar multiplication, right? Multiplication. So multiplication in Lean is called mul, but mul is when you're multiplying two things together. Mul would be the multiplication on the field K. So here we have a different kind of multiplication, right? We have an element of K and an element of V, and we want to multiply those together, and so it's called scalar multiplication and is abbreviated SMUL. SMUL mem. That would say that for all constants C and K, and for all V and V, we would have what? If V is in the subspace, that would imply that C times V is in the subspace. And the note, and you see C times V, this isn't going to work. There, this doesn't work. You see, it doesn't. This symbol here, multiplication, the two things, the left-hand side and the right-hand side of that multiplication, have to be of the same type. And these are not, right? C is in K and V is in V. So we use different notation in Lean. We use /bub. We use that funny dot there. So that's the end of the definition, right? So that's what a subspace of a vector space looks like. And in Lean's maths library, there is a huge interface developed for the theory of subspaces of a vector space. And I'm not going to develop that entire interface now, but I'm just going to show you how to start developing such an interface. I'm going to get as far as putting a lattice structure on the subspaces of a vector space, because we're going to be using the lattice structure when we prove our main goal, that the intersection of these two 5D subspaces is non-zero. So first of all, I need some machinery. What machinery do I need? So let's so theorems about subspaces are going to go in a namespace called subspace. In subspace. I should be looking at the chat. Sorry. Is anybody complaining about anything? I've got an extra arrow. You see. You, David, thank you. You want me to write this, don't you? There. If A is in the carrier and B is in the carrier, then A plus B is in the carrier. There you go. So, so that's David's version, and this would work fine. But what I've actually done, okay, so here's an interlude on currying, right? Interlude on currying. There. The idea is, what is a function? What am I trying to do? I'm trying to, yeah, you see this, you want me to write P and Q implies R, right? That's P and Q implies R. That's what we have here. But equivalent to this is the following, is P implies Q implies R, right? That's logically equivalent, right? Logically equivalent, because you could just, if you like, you can just draw a little truth table to check that P and Q implies R if and only if P implies Q implies R. And so that means that instead of writing P and Q implies R, which we could write, this would work fine, but I'm going to write it like this: P implies Q implies R. There, and that's logically equivalent. So we could write it that way instead. And now it turns out that this implication arrow, turns out that the implication arrow is right associative. There. And so that means we don't actually need the brackets. So there is our definition of a subspace. And sorry, I stopped looking at the. I need to fiddle around so I can see the chat and see everything else I'm looking at. I need about, if I had 3 monitors, things would be fine. Right, I think now we're okay. So let's make a basic API. Let's make a basic API for subspaces. So my goal is now to put a lattice structure on the subspaces. So I'll tell you what a lattice structure is in a second. But first of all, these I don't really want to talk about carriers because it just doesn't look very nice. So let's have some variables. So let k be a field. Let k be a field, and let k be a field. So let's have variables k. So that's how we let k be a field, and let v be a vector space over k. Oh, that might be. Let me put that in these brackets instead. And let v be a vector space over k. So I'm going to I think I'm going to do this as well. These squiggly brackets mean Lean should be able to guess what these things are. So V is going to be an additive commutative group, and it's going to be a vector space. KV. And let's let W and X be subspaces of V. So variables W and X. And they can be subspaces. Subspace KV. Great. So that seems like it's worked. And now what are we going to do? You see, and now it's a bit annoying at the minute. At the minute, if V is in V, I can't write V is in W because W is not a set, right? W is a quadruple. This is the thing. If W is a subspace of V, then W isn't a set the way I've set things up. W is a 4 tuple, right? W is 4 things. It's a set and it's 3 proofs, right? Just the same in group theory, right? A group isn't a set. A group is a set plus some other things as well. So I want to be able to write things like V is an element of W. And so I'm going to define, so let's define V is in W to mean kind of V is in the carrier there. V is in the underlying set. So instance has mem V subspace KV. So this means so what I'm saying is has mem, this is notation for is an element of. So what I'm saying is if I've got an element of V and I've got a subspace W of V, then it makes sense to say the element is in the subspace. And so this would be the function that takes an element of V and takes a subspace W, and then it returns true if V is in the carrier. There. And so now we've eliminated all these carriers. This means that these 3 axioms, 0mem, admem, and smallmem, don't look very nice anymore. We can do better than this. I'm going to put little primes on these things here. There. And now I'm going to redefine them. Now let's define 0mem. So this says that def. Let's define 0. So now we've got this nice notation. Let's use it. The 0 element of the vector space V is in W, and that means 0mem. Now I'll just put the primed, I think. There we go. So this is just boilerplate. Lemma add mem. Oh, did it not work? Lemma add mem So this says if A and B are in V, then A is in W and B is in W, implies A plus B is in W. And that should be add mem primed something 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 W A B. Bingo. So, oh, this isn't a definition, it's a lemma. So there's a lemma, and finally smellmem. And that says if C is in K and V is in V, V is in V, then what does it say? It says, which way round did I do it? I guess it was, it's just V is in W implies C times V. C times V is also in W, and that is smellmem. What? Smellmem W CV. There we go. So now that's just, this is all just notational nonsense. So now the next thing I want to do, so next step, prove that subspaces, why I'm doing this will become clear later. Prove that subspaces are a partial order. There. So why is that true? So i.e. I prove that subspaces are partially ordered by inclusion. There. And so partial orders have axioms, right? You know, partially ordered sets. You know, this is not just a case of defining some relation. These have axioms. So I can't just define subset and say now we're finished. But these axioms are already proved for subsets of V, right? I can show you that instance that partial order set V by apply instance. There. This line here, this slightly complicated computer sciencey line, says, can we prove that the subsets of V are partially ordered? And the answer is yes. A machine called the type class inference system already knows that. The type class inference system, whatever that is, already knows that subsets of V are partially ordered. There. And so we don't need to check the axioms really for the subspaces of V. Right, so the subspaces of V. Will automatically be should automatically be partially ordered, right? Get a partial order structure. But Lean doesn't know that yet, I suspect. Let's just try this here. Instance partial order subspace KV. You see there, the system doesn't know it. The system's not smart enough to guess what this is, because the system is completely open to the idea that I might want to define a totally different order relation on subspaces. It doesn't necessarily want to assume that I want to. So this is by inclusion, right? There. But the system doesn't know this. The system fails here because I might want to put a completely different partial order on the subspaces. But I don't, of course. I want to. What do I want to do? I just want to induce. I just want to induce this. Let's do this. So there's something called partial order dot lift, right? Let's check partial order. This is one of these things that you just have to know. You know this because I know what the interface for partial orders is. So this thing here, partial order dot lift, says that if I've got a function from x to y, these are just variables. If I've got a function from m1 to m2 and that function is injective, then I should be able to get a partially ordered function on m1. I can't see. Let's put this here. There. Partial order dot lift says if I've got two random sets, alpha and beta has a partial order, and then if I've got a function from alpha to beta which is injective, then I automatically get a partial order on alpha. So that's what this is the function I need to get a partial order on subspaces. So it's partial order dot lift, and now What do I need? It's complaining. Why is it complaining? I'm quite surprised it's complaining. Why are you complaining? Oh, I mean, maybe I should give it some data. Maybe I should say what the function is. So we need to say what the function is from the subspaces to the subsets. And of course, that's just carrier, right? That goes from subspace KV to set V. There. Oh, now we're in good shape. And now it says, okay, if that's your function, you've now got to prove that your function is injective, right? This is now the problem. I've now got to prove. So this is a theorem. So now we can go to good old begin end. So this is our first theorem. We've got to prove. What's the complaint? Oh, let's get rid of that. What have we got to prove here? We've got to prove that the function that sends a vector space to its underlying set is injective. So when you think about it, what does that involve proving? So intros W and X. So let W and X be subspaces, and let's assume that W and X have the same underlying set, right? Now you've got to prove that W and X are the same underlying subspace. And that's obvious, right? Because two subsets. Yeah, you see, we've got two subspaces that have the same underlying set. We've got to prove they're the same underlying space. So this should be easy, but what we're missing something. We're missing an extensionality lemma, right? Extensionality says that if two things are made from the same stuff, then they're equal. And this extensionality lemma can be automatically generated if I tell it when we make the structure. There. If we make that structure, I put this ext here. Now an extensionality lemma has been generated automatically. So we should be able to use the ext tactic there. And the ext tactic now says, now you've got to prove, now all you've got to do is to prove that a random element of V, let's do ext V. My goal now is to prove that a random element of V is in W if and only if it is in W's underlying subset, if and only if it is in X's underlying subset. But we have a hypothesis that these subsets are the same. So if I rewrite H, the goal, there we go. The goal now becomes to prove P if and only if P, which Lean does automatically. So there's the proof that subspaces form a partial order. Hello again. Hello again, Zane. Oh, how do I type the oh, it's sorry. /bub. Someone's got yes. Wonderful. Thank you. So now they're a partial order. So why are we doing this? So next I want to make subspaces of V a so-called lattice, right? So what is a lattice? It's a partial order with some extra struct with a min. Well, let's call it with a lub and a sub. So this is just for two elements, right? For two elements. So I need to make sure I have lub. I need to define lub of Wx. So V is going to be my vector space. So lub of W and X is the least upper bound of W and X, right? So what I'm claiming is that given two subsets of W and X, I claim that given two subspaces of V called W and X, my claim is that there's a least upper bound, which is another subspace, which is the smallest subspace that contains W and X, right? And we also want the greatest lower bound of W and X there. The greatest lower bound of W and X. So the greatest lower bound of W and X is supposed to be a vector space, which is contained in W and contained in X, and is the largest subspace with that property. So I guess we could do inf first. Let's do the greatest lower bound first. Let's do inf. So let's define inf. So we have W and X. They're going to be subspaces. They're going to be K subspaces of the vector space V. And inf of W and X is also going to be a subspace of, it's also going to be a subspace of K and V. And how are we going to make that subspace? Well, we have to look at the definition of a vector space. Let's click on that and click on that. There we go. So this is the job we have to do now. So I'm going to define this greatest lower bound of two vector subspaces of V. So W and X are two subspaces of V, and I want to define their inf, which is also a subspace of V. And so I have to say what the underlying set is. And of course, the underlying set is just the intersection, right? So it's W dot carrier intersect V dot carrier, no, X dot carrier. There. So that's the subspace. And now you see, Lean says, yeah, but we're not finished yet. You've got to prove these three axioms, right? I've got two subspaces. I've intersect. We've got to prove, you know, we're proving the theorem that the intersection of two subspaces is a subspace. There. So we've got to prove begin, end. We've got to prove that the intersection, there we go. See, we've got to prove that 0 is in the intersection of V and the intersection of W and X. So how are we going to prove that? So the definition of 0 is in some set intersects some other set. The definition of that is that 0 is in the first thing and 0 is in the second thing. So this is a well disguised and statement. So we can split that and statement. And now we've got two goals. We've got to prove that 0 is in W, and we've got to prove that 0 is in X. And we know that 0 is in W because that's an axiom, right? So we can apply W dot 0 mem, and that will prove the W one, and then we can apply X dot 0 mem. Where's it gone? X dot 0 mem. There. And you see now we've proved, you see now we've only got two errors. We've got two errors because there's two axioms we still have to prove. I can make those errors go away, look. Let's put sorries in here. Errors are bad. There we go. Now we have no errors at all. So this is a proof, that given two vector subspaces of a vector space, their intersection contains 0. So now we've got to prove that their intersection is closed under addition. There. So how are we going to do that? So let's say A and B are elements of the big vector space, and let's assume that A is in the intersection of W and X, and let's assume that B is in the intersection of W and X, and now I've got to prove that A plus B is in the intersection of W and X. So here's the problem we have here, right? We have two elements of V called A and B. A is in W and X, B is in W and X. I've got to prove that A plus B is in W and X. So I guess, what does it mean for A to be in W and X? It means A is in W and A is in X, right? So we can do cases HA with HA, HAW, HAX there. And similarly, we know that B is in W and X, so we can do cases HB. Cases HB with HBW, HBX. Oops, HBW, HBX. There, and now, so now we know that A is in W, A is in X, B is in W, and B is in X, and now we've got to prove that A plus B is in W and X. So we've got to prove that A plus B is in W and in X, so we do the same thing, we split, right? There, and now we've got to prove two goals. The first thing is we've got to prove that A plus B is in W, and of course we're going to apply, that's going to be exactly W dot addmem something something. What is it? Is it two things? Yes, we've got to prove that A is in W, H-A-W, and we've got to prove that A is in X, H-A-X. There, and it didn't work. Oh, that's because I've got to prove that B is in W. See, isn't it good? See, if I was giving a lecture, I would have got that wrong, right? And now this other goal here, I've got to prove that A and B are in X, and that's because A is in X and B is in X. That's HAX and HBX. And this statement here is the assertion that X is closed under addition. So that's the end of that. So now I'm going to give a, why don't I just, I don't know. So now let's do this one in a fancy way. So I'm going to use some more high-powered tactics just to get on. Rintros. So what have we got here? We've got C and V, and then we know that V is in W and X. Oh, no. What have I done? Comma. Let's put a comma. Rintro C, V. Aha. I know that V is in W and X, so I will just take that HVW, HVX there. Maybe put a comma there. And we also know, and that's it. And now I've got to prove that C dot V is in W and X. So I can do this like this. It's exact. I've got to prove two things. I'm just using more high-powered techniques here to get to, I mean, you could do it exactly using intros, cases, and split and exact. So now I've got to prove that C dot V is in W, which is W dot smallmem. W dot smallmem what? C HV HVW, and this will be X dot smallmem C HVX there. So that should be the end of that proof. Great. So we've just proved that the intersection of two subspaces of a vector space is a subspace. And there's our inf. And the next thing, so now what we can do is we can actually, and now we can make something called an inf semilattice, right? Instance semilattice inf subspace KV there. So that's a something that we make on the way to making a lattice. We make an inf semilattice first. And if I click on this, you'll see that what I have to do, well, we've proved all the partial order axioms. So I should be able to do dot dot whatever it was called, subspace dot partial order probably there. And we need to define, we've just defined inf, so I can put inf equals inf here, there. So the axioms for an inf semilattice, there's three axioms, and oh, now you see we've got this exciting new notation. So now we have to prove three theorems. Let me sorry them out. There. Because an inf semilattice is a partial order, which we have, with an inf, which we've just defined, but the inf has to satisfy three axioms. I could have defined anything here, right? I could have just defined the inf of W and X to be 0, right? There's no theorem there. There's just a definition. So what's going on here? Begin, end. What have we got to prove here? The axioms for an inf semilattice are we need to have some kind of thing called an inf, and they're going to use this inf notation, common in the theory of lattices. And so now we've got to prove that the inf of A and B is less than or equal to A. So how are we going to do that? I guess really, actually, we know this already because this is just a statement that the intersection of two sets is a subset of the left thing. I can be clever, right? I don't even need to go into tactic mode here. Let's take two subspaces, W and X, and this is going to be called set.intersubset left. Because you see, I know the API for subsets. Yeah, that's done that. So lambda W, and X, and this is set.intersubset right. Blank, blank, there. And LE, oh, what's LE inf? There's one more axiom we need to prove. And that axiom says for all subspaces A, B, and C, aha. So let's do this then. So intros W, X, and Y. Let's see what we've got to prove here. You see, Lean just keep the thing I like about Lean is Lean keeps track of absolutely everything that needs to be done. Here we go. We need to prove that if W is a subset of X and W is a subset of Y, then W is a subset of X intersect Y. And again, for sets, this is a triviality, and it has a name, I think. What's it called? I think it's called, this will be called something like exact set.subset inter, I think. Set.subset inter something. Oh, no. Maybe small. Is it small inter? Yeah. Set.subset inter blank, I think. No? Hard luck. Set.subset inter, is it this? Is it not that? Oh, it is that. There we go. Oh, it's fine. It's finished. There. So these turned out to be standard facts coming from set theory, but I'm not building an interface for set theory right now. I'm building an interface for lattices. And I think maybe I'm going to stop building that interface right now. maybe I'll get as far as a semilattice imp. That will do. And so now I'll show you what we have now. You see, now we have this, right? A semilattice imp comes with free notation, right? So we've got if W and X are subspaces, then what can I do here? And I can give you another subspace. Oh, this is the point. If W and X are two subspaces of V, I can give you another subspace of V, and that subspace of V is going to be W/greatest lower bound of, no, yes, W's intersect X. So there we go. So now we have notation there. This gives us notation for inf, namely glub there. And so this is lattice notation for intersection there, and the lattice notation for direct sum, for sum W plus X is going to be lub, least upper bound there, but we don't have it yet, right? I can you see bunk gunk gunk there. You see there's an error here, but I now have an error in my code, and the complaint is I haven't defined a supremum on subspaces. So I could spend another 15 minutes defining supremum by defining a function sup, which would the carrier would be the elements of V add the elements of W add the elements of X, and I could do all that, and it would probably take about 15 minutes, and then I could go on to define a top and a bottom, right? So you see I'm going to cheat, right? Now if I leave this, look, now I'm outside the namespace where I was building subspaces, and now I'm outside that namespace. I can just use sort of, look at this. So now let's do this. No, I don't have my I need to get my variables back. I've lost my variables. Let's put them back, because that was just an example of me building subspaces. So now let's go back. Now let's go back to Lean's subspaces there, because now you've seen that it's possible to build such a theory, and you see now this works there. So that's the intersection of two subspaces, but now lub should work as well. It does, you see. So using Lean's definition of subspaces, we were just recreating Lean's definition. We have four things now. We have glub and lub, and we also have top and bot there. And you can guess what top and bot are. Top is the biggest element of my lattice of subspaces. So top is just V, and bot is the smallest element of my lattice of subspaces. So bot is just the zero-dimensional subspace. So there is how to make subspaces. That's a hint, there's some ideas about how to make a theory of subspaces, but now we're using Lean's. Look, if I just right-click on subspace, go to definition, you can see here is my, oh, it's not, is it? Oh no, I see. Subspaces are defined to be submodules. So in fact, the whole theory is set up for submodules of a ring. And here, there we go. So here is a huge, interface for submodules of a ring. And we can just, it's all in the maths library. So we're going to take it. Let's go to Twitch. Right. So now finally onto the main order of the day, last 20 minutes, proving that intersection of two 5D subspaces of a 9D space is non-zero. So how are we going to do that? I guess, what do we have already? We have let K be a field and let V be a vector space over K. Okay, so let's and so maybe we don't need these yet. So the next thing we're going to need, do you know what we're going to need? the theory we were just working with there was there was no finite dimensional hypothesis at all, right? That whole thing would have worked for arbitrary vector spaces. But now we want to assume, let's assume that V is a finite dimensional vector space. Look, it's a finite dimensional vector space over K. So let's put in the additional hypothesis that this vector space is finite dimensional. So how would that go? That would go finite dimensional KV there. So now V is by hypothesis a finite dimensional K vector space. And I think that we are probably ready. So now let's prove that the intersection of two 5-dimensional subspaces of a 9-dimensional space is non-zero. Okay, so here's the theorem. Theorem, I don't know, 5 into 5. So what does it say? I guess it says, oh, well, maybe it says all of these things. What does it say? Let's say, firstly, it says we have a hypothesis that the dimension of V is 9. So fin dim V equals 9. And why didn't that work? Because I need to open finite dimensional there, and it's an underscore. Great. Okay, this is great. So let's assume that the dimension of V is 9, and let's assume that we've got two subspaces X and Y, subspace KV. And so that says so theorem 5 into 5 there. So assume V is 9-dimensional there, and X and Y are subspaces of V there, and dim X equals dim Y equals 5. So these are more hypotheses. HX can be the fin dim X equals 5, and HY can be the hypothesis that fin dim Y equals 5. There. And the conclusion is then, so we put a colon for that, then X intersect Y is not 0. There. And we're going to write this written using lattice notation, because the subspaces of a vector space form a lattice, and we're going to use standard lattice notation. So the conclusion is that X, the greatest lower bound of X and Y, is not equal to the bot, right? Oops. Bot there. And here's the proof. So how long have we got? Great, 15 minutes. So here's what we have. So K is a field, V is a vector space over K, which is finite dimensional. We're assuming, why does Lean write fin dim instead of dim? And maybe I'll just show you that. Let's put a sorry here because I don't like errors. Let's just check dim. Dim, is it vector space dot dim? Let's try vector space dot dim. It is. Vector space dot dim, the reason I'm avoiding vector space dot dim is because you can see down here that vector space dot dim takes as input a field K and a vector space over K, and it outputs a cardinal, right? Which is fine, but somehow I'd rather have a natural number, because we're in the finite dimensional situation. And of course, every natural number is a cardinal, right? So the output is a cardinal. And now there's some kind of type issues, right? Of course, every natural number is a cardinal, but nat subset cardinal. It's not that it's false. This makes no sense in Lie, right? Because these are types. You see, there's a map from the naturals to the cardinals, but I just don't want to get involved with that map. I don't want to, you know, I don't really be bothered with the map. So there's this special function for finite dimensional vector spaces called findim, and if I hover over findim, then you see that it returns, right? It returns a natural number instead of a random cardinal. And if you feed in, and this is a great example of garbage in, garbage out. If you ask what the finite dimension of an infinite dimensional vector space is, it just returns 0, right? But that's not going to be a problem for us because we're never going to ask it the dimension of an infinite dimensional vector space. Everything here is finite dimensional. V is finite dimensional. X and Y are subspaces, so they're also finite dimensional. Okay, so let's prove it. And the proof isn't so difficult because, as I say, there's a big interface for vector spaces in Lean's maths library. Maybe I also need to open Submodule because that's where we're going to use this. The theory of lattices is all developed for submodules. So the key result, right? Have key. The key result is that the dimension findim. What's the key result? It says findim k of x lub y, and I add this to, now why is that complaining? Curses. Do I need, let me do this. Let me do this. Let me do this. Submodule. The lemma I want, I happen to know the name of it. It's dim sup add dim inf. Dim sup add dim inf. Dim sup add dim inf ek. It's exactly that one. Yes. It's submodule this. So let's just see what this is. This is the theorem that we're going to use to prove this. So this says that for all submodules, which are subspaces, of course, I'm going to feed in x and y. There we go. So key result that dim. Let's just see what it says again. It says that dim of x plus y, add dim of x intersect y, there, equals dim x plus dim y. There. And as I say, that's already in Lean's maths library. So there is our result there. The dimension of x, whatever that says. I mean, you see it's using this lattice notation, which is why I went through this lattice stuff first. But what it really says is this. So this is our key result, and everything should be quite easy by now. So how are we going to prove that x intersect y is not 0? And you see, again, this is rather strange notation for 0. I mean, one could fix all this up by adding an extra notation, but I didn't bother doing this, unfortunately. So now what do we know? I guess we know that the dimension of, we know what this is, right? Hypothesis hx says the dimension of x is 5, and hypothesis hy says the dimension of y is 5. So we can rewrite hx at key, can't we? And we can rewrite hy at key. There. Oh, and it didn't work. That's a blow. What have I done? Everything has gone wrong. Oh, because findim. Because this takes a k. I'm sorry. This says that the k dimension of x is 5. Bingo. This says that the k dimension of x is 5 and the k dimension of y is 5. I'd forgotten to put those in, so things weren't working. So now let's go. Okay, right. I'm back on track. So this key result that we pulled out of the library says the dimension of x plus y add the dimension of x intersect y is the dimension of x add the dimension of y. And we know the dimension of x and we know the dimension of y. So let's substitute those in with the rewrite tactic. And so now we know that the dimension of x plus y add the dimension of x intersect y is 5 add 5. And 5 add 5 is 10, but Lean is quite happy to leave it as 5 add 5 right now because we didn't tell it to we didn't tell it to work anything out. I mean, we could do that if you like. We maybe do simp at key or something. I don't know how to do it. Norm num at key, that should probably do it. There, you see. So I've changed the 5 plus 5 into a 10. Norm num does arithmetic. You know, this is the arithmetic tactic. So now we know the dimension of x plus y, the dimension of x intersect y is 10. We're trying to prove that x intersect y is not 0. Well, I guess another key fact that we know from the library, have key 2. I mean, it's handy knowing your way around the library, right? Have key 2. This says that the dimension, the k dimension of x lub y. I don't know what this dimension is, of course, but one thing I do know about it is that it is less than or equal to findim kv. I think I need one of these funny arrows, don't I? Is it complaining that I'm not there? I think it might be complaining. What am I doing? Sorry, I'm failing to get. I'm rubbish at this kind of arrow. There it is. I want one of those arrows there, but I can't remember the shortcut for it. Does it like that? Yes. So why is this true? The dimension of x add y is at most the dimension of v. So I claim that dimension of x plus y is at most the dimension of v. And why is that? Because x plus y is a subset of v, right? There. And so there. And so the dimension of a subspace is at most the dimension of a space. And that is exact. I think it's apply findim le or something. Is that right? Yeah. Findim le, the dimension of a submodule is bounded by the dimension of the ambient space. So let's apply that. And did that go well? That's gone well. Great. So now you see we have key, the dimension of x add y, and the dimension of x intersect y is 10. And we also know the dimension of x add y is at most the dimension of v. And of course, we know what the dimension of v is, right? We can rewrite hv at key 2 there. And that's failed again, presumably for the same reason, yeah. There. Stated the problem incorrectly. So great. So now we know the dimension of x add y is at most 9. And now you can see we're in a situation where we're going to be able to prove this by contradiction, right? The dimension of x add y is at most 9. If this was true, if x intersect y was 0, then the dimension of x intersect y would be 0, and we'd have a number which is at most 9, add 0 equals 10, which is the contradiction we seek. So we're going to do this by contradiction. Are we? Let's do it. So let's assume that x add y is empty. So intro hxy. Let's assume that x intersect y is empty. And now we're going to need, what are we going to need? We're going to need the fact that the dimension of 0 is 0. Aha, I see. So now we know that x intersect y is empty, so we can substitute that into key, right? Rewrite hxy at key. There. So now key says the dimension of x plus y at the dimension of the bottom subspace, which is the 0 subspace, is 10. And I guess Lean will probably know what's the dimension of the 0 subspace. I wonder if the simplifier knows that. Simp at key. Let's try this. It does not. So I need to know, ho-hum, I need to know what the dimension of the 0 subspace is. And so I'm going to have to, my guess is that this is going to be called, let's try this. Rewrite findim bot. There it is. Findim bot. You see, so even though I didn't know that part of the API, I guessed what it would be called. Rewrite findim bot at key. So that applies the theorem that says the dimension of bot is 0. So now look, we now know that dim Yeah, now this is not looking good, right? So now we're in a situation, we know that the dimension of x plus y add 0 is 10, and we know that the dimension of x add y is at most 9. So this gives you a contradiction by just using, you know, a linear arguments involving linear inequalities. So I should be able to do this using the linearist tactic. And I've done it. Goals accomplished. I've got an exciting little thing that's apparently been removed from the most recent versions of MathLib, so hard luck. And that's the end of, I've finished the proof, right? There's no errors left. So there's what the proof looks like. There. If the dimension of V is 9, x and y are subspaces of dimension 5, then x intersect y is non-zero. And maybe I should tell you that actually this proof somehow, I said it was a proof by contradiction, but in fact the definition of x intersect y is not 0. The definition of not equals is if it's equals, then prove a contradiction. So really when I did this, you see my goal became false. And if a mathematician is trying to prove false, then of course they're trying to prove false by showing that their assumptions are false. And so mathematicians talk about this informally as a proof by contradiction, but strictly speaking, this wasn't a proof by contradiction, but I'm kind of splitting hairs. So there you go. So if you know about constructive mathematics, you would object to me saying that this is a proof by contradiction, but any mathematician would tell you that this is a proof by contradiction. I proved that something was not equal to 0 by assuming it was equal to 0 and getting a contradiction. So if that's not a proof by contradiction, I don't know what is. So I guess this was the key thing. We needed to know this key result here, otherwise it would have been difficult. But you see, this is quotes a result from the course, right? This is a result from the course. Oh yeah, someone's asking about these up arrows. I'm coercing. What's happening here is y has type subspace something, right? Y isn't a vector space, y is a subspace, but I want to think of y as a vector space, so I have to put this little weird arrow there. That little weird arrow means I know it's not a vector space, I know it's something else, but that something else is obviously a vector space, so just pretend it's a vector space. That's what's going on there. And I think that's all I have to say about this. I mean, you can see, I mean, this is somehow the issue, isn't it, right? But you see, maths lecturers are this is a fact you need. What would an undergraduate say? An undergraduate would say, oh, it's lemma 3.8, right? And lemma 3.8 is just as hard to, you know, lemma 3.8 is worse than this because lemma 3.8 is kind of lecturer dependent, right? It might be lemma 1.3 in some other course. So the fact that you have to learn some weird thing, I mean, I've seen students in my class, I've seen students write exam scripts that say, now this follows from lemma 3.8. I've actually seen people write that in exams. You know, fortunately I have the lecture notes so I can verify that that's, you know, that they've applied the correct lemma. So I guess this is something that one just has to learn. You know, if you're working in an area, then after a while you pick up the interface for the area. Or alternatively, you just learn the rules. I had to guess this one because I'd forgotten it. Findim bot. And Findim LE is also kind of obvious. I don't know. So anyway, that's how it works. And you can kind of do any undergraduate example sheet question of this level using this kind of technique. And it's 5 o'clock, so I'm going to stop. Thanks a lot for coming. And maybe I'll see some of you on Tuesday. Cheers.